Hello and welcome to today's class. Today we'll be looking at theory estimation. Under this class, we are going to look at methods of finding point estimators. And under the method of finding point estimators, we are going to look at method number one called the method of moment. And let us have a brief introductory about the method of moment, whereby from any form of a distribution, we must have to find the PDF, probability density distribution function, of that population distribution that we learned in the previous classes. We were able to look at the normal distribution, binomial distribution, we had Poisson distribution, and so many other distributions. So we must have to know the PDF of any distribution. Then, after knowing that PDF, for example, we have a PDF in this form, x with k parameters, say theta all the way to theta k. I.e., for instance, we have the population. The population will contain k parameters denoted by theta 1 all the way to theta k. That is the population parameters. And therefore, we wish to find the k parameters. Finding the k parameters, what we'll have to do is we let mu of the earth moment be the earth moment to be the earth moment about the origin for the population full stop. Then this means mu prime of earth moment should be equals to the expected value of x, but this x will be the earth moment. I hope you see. Let me now briefly describe how are we getting this. Initially, when we looked at the binomial distribution, normal distribution, let us look at the binomial distribution. We said the expected value of x should be equals to mu, and means the expected value of x is the same as mean. That is what we are briefly describing. Now, when we come back to now the earth moment about the origin, we shall say from this we shall have the expected value of x, but of x, because it's through the origin, all of it through the earth moment. So we are just repeating this one from this. So it should give us the mu of the earth moment. Are we there? So after we have now let there, we will let m be the earth moment about origin, or for the sample. And please note that the first one was for the population, but this one for the sample. Then i.e., it means m of the earth moment should give us 1 out of n, the summation of x I earth moment when I is heading to 1 all the way to n. I think this what I'm trying to mean is, initially in the previous class we learned that mean, which is always from the sample population, is x bar, represented by x bar. That is what we are representing by m, is always equals to x1 plus x2 plus x3 up to xn all the way to n, right? So if we rewrite this one, we shall have x bar is equals to, because it's 1 out of n, then the summation from I heading to 1 all the way to n, capital X. When we say capital X, it means the summation of all sample mean from x bar. Then that is what we are just implying from this. Now, I hope you have understood that. Now we say the expected value of x being equals to mu is the same as mu prime of the earth moment, which is the same as the expected value of x earth moment is equals to mu earth moment. So to get the method of moment estimators, getting the method of moment, we always equate the first moment to the second k moment. For instance, at my case, I will say mu of the earth moment should be equals to m earth moment. So we are going to look at those two moments. The first moment we got it as mu prime of m earth moment. The second moment we got it this way. So to get the method of moment, we always equate the two. Let me hope you are getting it clearly. Now, let us now briefly look at how we finish this thing. So generally, from theta 1 to theta k is the same as theta 1 to theta k is the same as method of moment estimators. Now, briefly, let us look at a very, very short example for us to understand what we have just done. Given a question, obtain the method of moment estimator for a Poisson distribution, population distribution with parameter lambda. Now, if you have been asked to obtain the method of moment with the parameter lambda, we always say the first step when we were deriving the method of moment, we said we must have the probability density function of that population distribution. So at our case, our PDF is f of x lambda because it has parameters lambda. The first one we said x with theta 1 to theta k, of which we were not more specific. But when we come to a Poisson distribution, we have a very, very specific parameter is equals to the exponent negative lambda. Then we say lambda raised to x all over x factorial. That's what we are looking at. Now, we now look at how can we obtain mean, because when we look at these things, we were looking from the derivation of mean. So if we say mean from a Poisson distribution, we used to calculate by saying the expected value of x is always equals to the summation of x, f of x. So when we say f of x is the PDF of the distribution. Now, at my case, this is our PDF. Then this x will remain constant. Then I will have the summation of I heading to 1 all the way to n, x dot, what is my PDF? E negative lambda, lambda raised to x out of x factorial. Whenever I reach there, I have to rewrite x factorial. X factorial can also be written as x in bracket x minus 1 factorial. So let us substitute x factorial with this one. So we shall have the summation of I heading to 1 all the way to n, x exponent negative lambda, lambda x out of x into x minus 1 factorial. Then x and x will cancel out. Then this e exponent negative lambda is a constant, so we'll have to eliminate it out first. So we shall have it as exponent negative lambda, the summation of I heading to 1 all the way to n. So I have lambda my out of x minus 1 factorial. Now, this is where a critical challenge comes in. Once we are done like that, this one, the whole of this one can be written into this method. It's going to be this way. We are going to write this one as exponent negative lambda. Then in bracket, we shall have lambda out of 0 factorial plus lambda squared out of 1 factorial plus lambda cubic out of 2 factorial all the way to lambda raised to n out of n factorial. So when we reach there, we have to multiply through by lambda. When we multiply through by lambda, we are going to have lambda exponent negative lambda in bracket. We shall have this one, I think, will elapse. Then we shall have it as 1 factorial plus lambda out of 1 factorial plus lambda squared out of 2 factorial plus all the way to lambda n out of n factorial. So upon reaching there, what we have to do is now to see this, but the whole of this one is the same as exponent lambda. If you add the whole of this one is exponent negative lambda. So my expected value of x is equals to lambda exponent negative lambda exponent lambda. So this one brings us now to the laws of indices, whereby when we have two functions with the same bases multiplying each other, then we shall add the powers. So if we have the two constants, the powers are the same. The powers, we add the powers because the bases are the same. So we shall have it as lambda, because negative 1 plus 1 is just 1. So it is just lambda. So if we have now finalized by reaching there, we shall say, now let us look at second moment. The second moment is always, because the variance is always what we normally say the second moment, but variance is always also lambda for a Poisson distribution. So there is no need for us to go further and simplify many things, but we shall rather say second moment is the same as x bar. So this one implies that mu prime, the second moment, is the same as mu, which is the same as lambda. That is for the sake of a mean. Then our second moment, we have said, is the same as x bar. Therefore, equating the two moments, this means that mu is the same as m prime, right? And this one is lambda is the same as x bar. We are just equating this one and this one, right? This one and this one, right? Thus, our method of moment lambda is the same as x bar. Then you have finalized everything. I hope you've enjoyed your lesson. And before you switch off to this unit, please remember to subscribe so that in case of any new information about this unit, you'll be the first one to be notified about the content. Thank you and bye-bye.